Okay, so the last lecture of wave mechanics, we have looked at the general equation of wave, harmonic wave as a special case of that and all that. Then we have understood propagation speed in terms of physical properties of the medium, that is tension and medium mass density. These kind of things. The relation to power also we've discussed. So let's continue from that point onwards today. So transverse one-dimensional harmonic wave produced by a simple harmonic oscillator as the source. So we saw that along a string we have the sinusoidal shape that travels with respect to time. So the snapshot picture of y versus x at any instant is a sine curve. The general equation is of this type, depending on the direction in which the wave is moving. So this type, where omega is dependent on the frequency of the source and A is equal to omega by V, where V is square root T by mu. So propagation speed depends on the medium's physical properties. That is the tension and the linear mass density. And of course, that gives us this relation. So this also. And we have the general relation that the power transmitted to the wave is half mu v omega square into a square, or write that as square root of tension into linear mass density into omega square into a square. Okay, so this is the essential point at which we had discussed last time. Okay. Now let's also talk about. So we have also seen particle velocity and all that. So del y by del t, the particle velocity is the omega cos, and particle acceleration minus omega square y. So these terms are also there. Okay, now the significance of the phase constant. Let's understand that. The phase constant phi, that is in such a way that the value of the displacement, the transverse displacement at the point x equal to 0 at t equal to 0, you can see is a sine phi, whereas the particle velocity del y by del t at x equal to 0, t equal to 0 is e omega cos phi. So these two become essential in determining the value of phi. Just like in SHM, we had seen that initial position and initial velocity together tell us the value of phi. Because phi can be in any one of the four quadrants. So accordingly, whether sine phi and cos phi are both positive or both negative, or one of them is positive, one of them is negative, and so on and so forth. So let us see example of application of this concept over here, determining the phase constant and all these things. So this is a bit of a crucial part of wave mechanics. So make sure that you're paying attention and making all the questions and all clear, examples and questions and all. So anyhow, so let's say that we are given the snapshot picture of a wave at some time t equal to 0. That is given to us as a diagram. So the information given in the question is in the form of the diagram. This is y in millimeters, this is x in meters. And now I'm going to draw the snapshot picture of the wave, which is like this. This is the snapshot picture. This is the snapshot picture of a harmonic wave at the instant t equal to 0. Where this is 6. Initial value is half of that, let's say 3. Amplitude is 6 millimeters. Also, this value of x is given to us as 9, and the propagation speed is given to us as 100 meters per second. The wave is traveling at a speed of 100 meters per second. So, given the snapshot of a harmonic wave, determine amplitude, frequency, wavelength, omega and k from this. Write the equation of the wave and determine the particle velocity and acceleration at x equal to 0 at the instant t equal to 0. Third part, recalculate second part if the wave is traveling along the negative x-axis instead, but at the same speed. So this is a bit of a tricky question in sense that hidden information. Okay, this value here is 9 in meters, but you can see that is not half a wavelength because x equal to 0 is not at y equal to 0 at t equal to 0. So to be a little careful when you adjust that information and determine the value of phase constant according to how the wave is moving. And from that you also determine the particle velocity and the particle acceleration at the point x equal to 0, t equal to 0. So the hint that I would give you is for calculating the frequency, wavelength and all this, first compare the given diagram to a standard sine function and try to understand the significance of that distance between the points 0 and 9. In terms of lambda, what is the value of that distance of 9 meters? To try to understand that by comparing the given graph with respect to a standard sine graph, then you will understand that. Okay? And then once you've got lambda, then you can determine frequency because V is given. Okay, so that first part gets done that way. Amplitude, obviously, you can see in the diagram. Now, second part, when you are determining the equation of the wave, including the phase constant, you have to be a little careful about the value of phase constant because you have to understand that the wave is traveling along the positive x direction. Okay, so how the particle velocity is at x equal to 0, t equal to 0, that also has to be taken into account. Okay, people. So now let's take care to understand this relation between the wavelength and this. Okay. So I'm going to draw a series of graphs. Compare this given graph with the standard sine graph. Then compare it with the standard sine graph with a transformation. And then finally compare the graph of this one. Understand the wavelength. So if we have the standard sine graph, let's say that's something like this: y is equal to sine theta. So this point is theta equal to pi by 2. And the point where it's 0.5, the value of y, that point you can see is pi by 6. So now if I bring this point to the origin, I have to transform the graph in such a way that now looks this, let's say, okay. So I have transformed it in such a way that transformed it by pi by 6 units like this. So this has become the graph of y is equal to sine of theta plus pi by 6. So that this point now has a value of 0.5. And this point will now become how much? It will become pi by 3, where it becomes 1. So now if I look at the graph of y is equal to e sine kx type. So e sine kx plus theta, it's transformed, plus 5 or whatever. Kind of thing. Then this graph should look so if this point is e by 2, this point is e, then this value of x1 and let's say this value of x2. So here this point is pi. So this point will become 5 pi by 6 because I have transformed everything by pi by 6 backwards. So now basically what has to happen is that this value has to be such that kx2 is equal to 5 pi by 6. This value has to be such that when multiplied by this thing, it gives us this difference, pi by 3. This is 5 pi by 6. Okay. So this x2 corresponds to that 5 pi by 6. So now in the given graph, this value x2 is given to us as 9 meters. So therefore, kx2, which is 2 pi by lambda into 9 meters, should be equal to 5 pi by 6 is the idea. So lambda accordingly should become 10.8 meters. This is the equation of the snapshot at p equal to 0. This is this, and p is 2 pi by lambda, so 10 pi by 54 radians per meter. Okay, so compare this graph now, sine theta plus pi by 6 graph with this one. So here you can see that phi is equal to pi by 6. Okay. And therefore kx2 plus phi should be equal to pi now, because this point corresponds to this one. Just like in the first sine graph, this point at which y becomes 0 again is theta equal to pi. So in the second one, this point is which one? This point is one where theta plus pi by 6 is equal to pi. So that's how we are getting this point here as 5 pi by 6. Now correspondingly, kx2 has to be equal to 5 pi by 6. Understood? Then the wave speed was given to us in this direction. It was 100 meters per second. So use the fact that v is equal to f lambda. The frequency will come out to be 100 by 54 by 5. So 500 by 54 or 250 by 27 hertz. It's okay to have an odd sort of value of frequency like this, because it just means that in 27 seconds, it completes 250 cycles. Per second, it does not complete a whole number of cycles, but every 27 seconds, it completes 250 cycles. So omega comes out to be 2 pi f. So 500 pi by 54 by 27. Radians per second. We got the value of k, we got the value of omega. Amplitude was already given in the question indirectly through the diagram. It's 6 millimeters. We've got amplitude, we've got angular wave number, we've got angular frequency. Yes. Sorry. Why? Just a moment. We have. Oh, sorry. Yes. It's double of this. Yeah. Just make a correction. It's the wavelength is double of this actually. It's 108 by 5 meters. So it is. Okay, so hope the values are all right now. Okay. Now we come to the slightly tricky point that how we are writing the wave equation. Okay. So for the second part, the wave is traveling along the positive x direction. So let us say, suppose we write the wave equation like this: y is equal to e sine. Suppose we write it like this: omega t minus kx plus phi. So then our particle velocity is e omega cos omega t minus kx plus phi. Now, from the wave, what we can see is that it's not just about the position at x equal to 0, t equal to 0. It's also the direction of motion. So what is happening? The wave is traveling in this direction. So next moment, the wave will be like this. This will be the picture at delta t time, because this is the snapshot picture at t equal to 0. The particle at the
वो एरिया का कितना कोई वाला पैसा कुछ माल का उल्टी कर दी
it's having a particle velocity which is downwards. Okay, the point at x equal to 0. So you can see that y at x equal to 0, t equal to 0 was plus 3 millimeters. So that is telling us that according to this wave equation, e sine phi should be equal to e by 2. So phi should be sine inverse half. But as you know from SHM, this has two solutions. Okay, so we still also need to understand what is the particle velocity at x equal to 0, t equal to 0. And that is a omega cos phi. And that is what kind of quantity? It is a negative quantity. Okay, Snikita, I will show the question once more. Okay. So according to this, cos phi should be negative. So sine phi is half and cos phi is negative. So these two things together tell us that phi is equal to 5 pi by 6. So if we write the equation this way, it would be that it is 6 sine omega, which remember was, I think, 250 divided by 27, right? Yeah, 250 pi divided by 27. T minus kx. Now k was similarly k's value was 5 pi by 54. So that comes here. X plus 5 pi by 6. This is one way of writing the equation. There's another way of writing it also, and we will see that both trigonometrically as well as by using the initial conditions. Anyhow, so just taking you back to the question once. Okay, so let's come back to this. Okay, so this was the first thing, Snikita, that we determined the wavelength. And then from the wavelength, the frequency, because the wave speed was given to us. Just make a quick run through of this part also. Might have missed this. And then we'll come to the final part where we're determining the phase constant. Yes, Aditya, I'm scrolling down. Aditya and Aman, both of you. Okay, just a moment. Okay, so this is one way to approach the question. Okay, now another way to approach the question is we could have also started with the wave equation being like this, that we take the general equation as A sine kx minus omega t plus phi. The important thing is that the sign between omega t and kx has to be negative because the wave is traveling along the positive x direction. It has to be either kx minus omega t plus phi or omega t minus kx plus phi. Both will do for writing the general equation, but the sign has to be negative because the wave travels along the positive x axis. So if you start with this, you'll see you'll get a different equation compared to this one. You'll get a different phase constant, but the equation is equivalent. Here we are getting the equation of this type: E sine omega t minus kx plus 5 pi by 6. Here we'll get a different equation. We'll get a kx minus omega t plus some phase constant. Now that is where you have to be careful between the two. Okay, so same thing if you start with this, you get del y by del x, sorry, del y by del t is minus a omega cos kx minus omega t plus 5. In this, what we get is and you look at the snapshot picture and you still understand that the particle velocity at x equal to 0, t equal to 0, which according to this equation now is minus a omega cos phi, that is a negative quantity. So according to this, cos phi should be negative. So if I go with this notation here, then the cos phi should be positive. So phi should be in first quadrant. Here we had phi was in second quadrant. So phi will come out to be pi by 6. So this will now give us that y is equal to a sine kx minus omega t plus pi by 6. You can see that this equation is the same as this equation. These two are equivalent because you have to just use the concept that e sine pi minus alpha is equal to sine alpha, and then substitute the value of alpha as this whole thing, kx minus omega t plus pi by 6. So you get, substitute alpha as this. You get this whole term pi minus alpha as omega t minus kx plus 5 pi by 6. These two are the same things. So basically what is happening here is that sine omega t minus kx plus 5 pi by 6 is the same graph, is the same relation, same function as sine kx minus omega t plus pi by 6. And in fact, that is also the same thing as cos of omega t minus kx plus pi by 3 and other such terms also you can. So this is where things can get a little bit complicated when you're looking at the JEE Advanced type of questions to do with wave equations, and you have multiple options and all that. One has to be really very careful with this. Okay. So now also try the last part of the question. If we are assuming the wave to be traveling along the negative x direction, then what kind of change we make to the equations? Very good, Naman. That's correct, because now you can see that if the wave is traveling along the negative x direction, then the particle velocity at y is equal to 0, sorry, at x equal to 0, t equal to 0 will change. It will be upwards. So del y by del t at x equal to 0, t equal to 0 will now become a positive quantity instead of negative, because the wave is moving in a different way now. It's traveling. This is our snapshot picture at t equal to 0, but the wave is traveling along this direction. So now this will become like this. So the particle velocity is upwards at this point. This particle is going upwards in this way. You can see that y at x equal to 0, t equal to 0 is plus a by 2, and del y by del t at x equal to 0, t equal to 0 is positive. Now for a wave traveling along the negative x direction, this sort of a wave, we write the equation as, general equation as a sine kx plus omega t, or omega t plus kx plus 5 over. So del y by del t, particle velocity, becomes a omega cos kx plus omega t plus 5. So this thing tells us that e sine phi is a by 2, and this thing tells us that a omega cos phi is positive. So sine phi is plus half, cos phi is positive. That means phi should be pi by 6 in first quadrant. So if the wave was traveling in the negative x direction instead, then we will have to write it as a sine omega t plus kx plus pi by 6. Omega was 250 by 27 pi and pi by 54. Now, one more thing we have to do in the question, we have to determine the particle velocity and acceleration in the second part. Okay, this is the third part. So I'll come back to the second part and do that. But that's quite simple actually. We just substitute the values. It's nothing big. Okay, so let's understand the particle velocity and particle acceleration in the second part. Okay. Coming back to the second, this is the third part, the wave is traveling along the negative x direction. On the second part, the wave is traveling along the positive x direction, and I want to write the wave equation. We come to this. Okay, now from this we can see that particle velocity will become k omega cos pi pi by 6. So it is minus root 3 by 2 k omega. And we know a and omega, so we can calculate it directly. And del 2y by del t square, or the particle acceleration, is basically just minus omega square into y, and y was a by 2. So this practice at x equal to 0, p equal to 0, the value of y was a by 2. That's something quite simple. Okay, understand this here. Okay, so a little bit more about general equation of wave here, power and all that. Okay. Now moving on to another aspect. So we will look at superposition of waves. And right now we're talking in context of one-dimensional transverse waves. We'll later expand this idea. Mechanical waves. Yeah. So this will, now the first type of superposition we'll study is something called interference. So interference is a very specific term that is used when multiple waves of, very important, identical frequency, so traveling along the same string in the same direction, on a string, they overlap, superimpose. So when this happens, the superposition of this type of specific waves, that is, they are traveling in the same direction and they are having the same frequencies. So when such type of waves superimpose or overlap, the resulting phenomena, which we'll study in detail now, is called interference. So this is a definition of interference, which is contextual to one-dimensional transverse harmonic waves. So the condition for interference to occur as a phenomena is double, that over here. Two things, that same frequency and traveling in the same direction of the wave. So we can think of this like an experimental example, that suppose on the same string, which is infinitely long, we've got two sources doing harmonic oscillators of frequency f, amplitude a1, and another source here of frequency f but a different amplitude a2, which are creating disturbance along the y-axis. This is creating a wave of its own. So y1, this is creating another wave of its own. So y2. Now these waves are having common frequency. So S1 and S2 are simple harmonic oscillators attached to sine spring and oscillate at identical frequency f. So the waves produced by them individually let's say something like this. But deliberately I've taken the phase constant to be 0. String has tension T and linear mass density. So now the wave created by the second source will be maybe a different amplitude, but the same value of omega because it has the same frequency and therefore the same value of x, rather k. But it might have a phase difference because they're not in phase. Where phi is the phase difference between the value of y1 and y2 at any point x equal to x at time. So look at some position here, x equal to x. At some instant of time t, the disturbance created individually by the two sources would be something like this. Okay. So then the superposition of these two waves at any general sort of point p results in this kind of situation. Okay. So when we solve this mathematically, adding these two equations, we'll see we'll use the same technique that we've done in combination of SHMs. Okay. And it will give us a result which is like a phasor addition, very reminiscent or very similar to the vector addition that we've seen earlier. But here, of course, we are not adding any vector quantities. We are adding transverse displacements along the y-axis. So the direction is fixed. It's not a variable direction. So I will just I'll take you back to the earlier section so you can just note down this introduction to just make a quick note of it. I think it's already. And then let's come to the main part, which is the solving of this final equation that y is equal to y1 plus y2. Okay, let's continue ahead with this calculation now. So some of you might have worked it out yourself by now. Okay. So when we substitute these, we have a1 sine omega t minus kx for this one plus a2 sine omega t minus kx plus 5. So in this is a quantity which is a variable. Everything else is a constant. Let's take omega t minus kx as alpha. So this can be written as a1 sine alpha plus a2 sine alpha plus 5, which can further be expanded as sine alpha cos 5 plus cos alpha sine 5. So this becomes a1 plus a2 cos 5, which is a constant basically, into sine alpha plus a2 sine 5, which is again a constant, into cos alpha. So this time let's take this thing as a constant. Constant. And let's take this thing as another constant. This becomes of the type e sine alpha plus e cos alpha. Now you know how to deal with this. Multiply, divide by root of b square plus b square. Then express it as sine alpha, let's say cos beta plus cos alpha sine beta. Where you can see that cos beta is a upon root of a square plus b square. Sine beta is b upon root of a square plus b square. Finally, this becomes root of a square plus b square into sine of alpha plus beta. So with this on, now we can basically write this as y is equal to some net amplitude into sine of alpha, which is omega t minus kx, plus some phase constant beta. Because in this you can see that root of a square plus b square becomes the net amplitude, and alpha is equal to omega t minus kx. So now we can understand that the net amplitude, when we substitute a and b, small a and b over here, we get a1 square plus a2 square plus 2a1 a2 cos 5. And beta we will get as tan inverse. See from here that beta can also be written in terms of tan. So it is tan inverse of sine by cos, so p by p. So this becomes a2 sine 5 divided by a1 plus a2 cos 5. This comes here by just substituting a and b. So we substitute a as a1 plus a2 cos 5, b as a2 sine 5. So this and this will give you this and this. Okay, so now having understood this, this becomes the standard formula that we use from this one. And as I told you that sometimes the easy way to remember this formula or remember the actually even do the calculation for the net amplitude, the easy way of doing it is by just using a phasor diagram. Saying that it's a phasor addition. This whole operation can be represented by this kind of phasor diagram. So let's look at an example based on this numerical example. Generally speaking, using the phasor diagram method is the easier way of calculating the net amplitude in interference. Of course, remember the condition for interference is that frequency should be same for both the waves. Without that, we will not get the interference condition itself. So hope this part is clear to all of you. Now let's look at the calculation of phase difference, actually how it depends on various other factors. That is the critical thing in solving questions, etc. So phase difference, fine. It can be created by path difference traveled by each wave. The respective source to the point P at x equal to x. For example, if the source S1 is here, the point P is here, and this is traveling a distance x1 from here to here, and this point S2 is the source S2 is here, and the wave is traveling a distance x2. You can see the path difference x1 minus x2. This can create, this contributes to the phase difference because of this. And secondly, can also be due to an initial phase difference between the sources S1 and S2. So this is the situation where we understand that S1 and S2 must have same frequency, but they need not be in sync. They need not be synchronized. So that can also create phase difference. So now we will understand this with a numerical example. How to do these calculations. So this is a string which has a given tension equal to, let us say, 1000 newtons and a linear mass density of or tension of 100 newtons. A linear mass density of 0.1 grams per centimeter. Now what we are doing is on this string, we have two sources S1 and S2 which are located at x equal to 0 and x equal to d. There is a distance d between them. So S1 and S2 frequency 50 hertz each. Create waves amplitude (1.2 millimeters and 1.6 millimeters respectively. So the first part, if S1 and S2 are in sync, that is both started simultaneously at t equal to 0 from mean position with their initial phase constant as 0. Then, and also the value d given to us is 0.5 meters or 50 centimeters. Then write the equation of individual weights produced by S1 and S2 and find the net amplitude by their superposition. At some point P, which has a position given by x greater than t. So it's not between the two sources, it's to the right of source S2. So both the waves are traveling in the same direction as they superimpose at that kind of point. So you'll see here that while both the sources are in sync, but the waves that they create, they do not reach the point P in sync, okay, because they're traveling through different distances. So I just wanted to just excuse me, understand this point about phase difference first, and then come back to this question. Note down any key points if required.
I'll be back in 10 minutes. I'm just dumping the laptop. So let me buy will go later.
You want me to send Shamim back?
No, I'll come back. You can just leave the laptop.
Okay, people, I'm taking you through the question now. So all the data in the question is important. So if you just do what I've asked you in the first part, the A part, in first part's A, write the equation of the individual waves. By writing the equation itself, you'll understand how to calculate the phase difference. And from that, how you get the net amplitude in the second part. Just try this out. Okay, people, let's pay close attention to this and understand this question. So first of all, what is happening here is from this data, you can calculate the speed of the wave, the propagation speed, reduce it to SI units, it's 100 meters per second. So you can see that while the frequencies are 50 hertz, so V is 100 meters per second for the wave, frequency is 50 hertz. So lambda is V by F, that becomes 2 meters. This is the important information beforehand. So now suppose the simple harmonic oscillator S1 has a displacement given by E1 sine omega t, and the simple harmonic oscillator S2 has a displacement given by E2 sine omega t. Then at the point P, x is equal to x. Now this one is located at x equal to 0. This one is located at x equal to t. So the wave from this one is traveling a distance of x to reach P. But the wave from this one is reaching by traveling a distance of only x minus t. So at the point P, the equation of the wave, individual waves from these are going to be from S1, the displacement wave will be omega t minus kx, where omega is 2 pi f, so that's 100 pi radians per second, and k is 2 pi by lambda, so it is pi radians per meter. And the wave from S2, on the other hand, is going to be very similar equation, but we will have to replace x with x minus b, because it's just traveling a distance of this much. So you can see that then y2 will be of the type plus phi, where phi is 2 pi by k into d, 2 pi by lambda into the path difference delta x. So the phase difference and the path difference have this relationship. So in this case, now we can see that for d given as 0.5 meters and t equal to pi radians per meter, the phase difference is in fact becoming pi by 2 or 90 degrees. So this in fact becomes k2 sine omega t minus kx plus pi by 2. So this can also be written as k2 cos omega t minus kx. So that's the first part done. We've written all the terms. We've identified the value of omega, the value of k, we have seen A1 and A2. But most importantly, the phase difference here is coming pi by 2. It's coming from the calculation of this, but its value is coming out 2 pi by 2. So now we can see that the corresponding phasor diagram will show you that the amplitude should become 2 millimeters in this case, because the phase difference is 90 between 1.2 and 1.6. When we superimpose y1 and y2, it will result in interference because they are waves of same frequency traveling in the same direction, and result in a net amplitude which you can see will become 2 millimeters. Just a minute, we will complete this. Then we'll do another interesting second part of this question. I'll drop it. So we can see that the net amplitude here will become, because this will result in the net amplitude the root of k1 square plus k2 square. You can also see that this phase constant will become 53 degrees. So in fact, if you want to write it in detail, this will be the wave equation at the general point. So that is about this part. Now we will see another interesting aspect of phase difference. What if the two sources had not been in sync? So let's try to understand what happens in that case. So second part, again, that distance d is taken as 50 centimeters only, but this time S1 is started after a delay of delta t equal to, let us say, frequency was 100 hertz, so we take the delay as 7.5 milliseconds compared to S2. So now find the phase difference of the waves and determine the net amplitude. Remember, S1 was the one which was at x equal to 0. S1 was the source which was at x equal to 0. This is the source at x equal to d. Now, this is started at t equal to 0, but this is started with a delay of delta t. So, as a result of that, what is the net amplitude at this point? We have to calculate that. So just try this out, people, and through this, we will understand that if the two sources are asynchronous, that is, they're not synchronized, then that timing difference between them, how that can contribute to a phase difference also. So this is a crucial part of wave mechanics, okay, and especially like in sound also this will be very important, and later in wave optics also. So this is a critical part of this chapter. Okay, so let's quickly finish this. I'm aware that there's the class coming up for regular. For me also. Okay. So what we'll see here is that the equation for this one, the first source, will be that y is equal to a1 sine omega t minus delta. And the equation for the second source will be a2 sine omega t. So they are having a phase difference. The sources are having a phase difference of, let's say, phi naught, which is omega delta t, in which you can see that S1 is behind in time by omega delta t, which is 100 pi into 7.5 milliseconds. So you can see it is 3 pi by 4. And now you can see that the wave at t from S1, the wave will be a1 sine omega t minus delta t, but minus kx because it's traveling a distance x. But the wave from the second one, it is a2 sine omega t minus kx minus d. So something like this. So we can say that, like y1 is like a a1 sine omega t minus kx minus alpha kind of term, and y2 is a2 sine omega t minus kx plus beta kind of term, where alpha is equal to omega delta t, which we just saw as 3 pi by 4, and beta we've seen before is kd, that was pi by 2. So as a result of that, now you can see that the net phase difference is like beta plus alpha. It's your two phases like this. This is alpha. This is beta. See that the phase difference alpha plus beta. The net amplitude this kind of net amplitude. This might give us something calculation heavy at this stage. So don't worry about that. The important thing is the conceptual thing, how we got the phase difference when there is both the asynchronicity between the waves, between the sources, okay, as well as the path difference of delta x. So this is an important aspect of waves. Okay. So people will conclude our session here today. We have another session this week, which is very important because I need to go a little quicker with waves now. So next session we will look at more examples of superposition, and then we'll of interference, and then we will look at the second type of superposition, which is standing waves. And through that we'll see the resonant modes of vibrations of a stretched string. So that will complete this chapter, and then move on to sound after that. That's it for today's session, people. Thanks for attending, and wish you all the best.
Thank you, sir.